My name is Michael Nelson, and I'm going to be presenting a topic for my algebraic number theory class at Clemson University. This presentation was inspired by Keith Conrad's expository notes over the same topic. So let me just explain, let me just begin right here. So in this presentation, I'll be describing a relationship between conjugacy classes of matrices with integer coefficients and O-ideal classes of fractional O-ideals where O is an order in a number field. So if you don't know what those are, you're not familiar with that, don't worry, because I'm going to go over some of that real quick. So let's begin with some, let's recall some terminology here. So first, for conjugacy classes of matrices in M sub n of z. So let A and B be matrices in M sub n of z. We say that A is conjugate to B, and we're going to denote it by this A sub tilde sub C here. A sub tilde sub C, if there exists a U in GL and Z such that UA, U inverse equals B. It's straightforward to check that this tilde sub C is an equivalence relation, and we'll denote the equivalence class of a matrix. We'll denote by bracket A sub C to be the equivalence class, which is represented by the matrix A in M sub n of Z. So we call these equivalence classes conjugacy classes. And we'll denote by C sub n of Z to be the set of all conjugacy classes of matrices in M sub n of Z. Now, if you have the characteristic polynomial of a matrix A is defined by chi sub A of t equals determinant of t I sub n minus A. And if A and B are conjugate, so that means that there exists a U in GL and Z, so say UA, U inverse equals B. Therefore, when we do this calculation here, you see that chi sub B of t is equal to chi sub A of t. So what I'm saying here is that if A and B are conjugate as matrices, then they have the same characteristic polynomial. This is pretty well known, and it follows from this calculation here. So it makes sense to assign a characteristic polynomial to a conjugacy class of matrices in M sub n of Z. So for any monic polynomial f of t of degree n, we will denote by C sub n z comma f to be the set of all conjugacy classes of matrices in M sub n of Z with characteristic polynomial f. So let me just summarize real quick. So this is, okay, so first, okay, let's get up here. Okay, so first we have, so C sub n, we first introduced C sub n of Z. This was the set of all conjugacy classes of matrices in M sub n of Z, but we're going to be interested in not this guy, it's a little bit too big. We're going to be interested in this guy right here. So C sub n of Z comma f, right? So that's going to be the one that we're going to be interested in. And we're going to find a nice bijection between this guy and some other guy that we're about to introduce. So anyways, let's continue on here. So now let's recall some terminology regarding fractional O-ideals. So let O be an order in a number field K. So that means that O is a subring of K. It's finally generated as a Z module, and it contains a Q basis of K. So in our interest, actually, the order will be something like Z adjoining alpha, where alpha is an algebraic integer over Q. So that's the one that we're going to be mostly focused on in this presentation. A fractional O-ideal is a non-zero finally generated O module in K. So let I and J be two fractional O-ideals. We say I and J are equivalent, denoted, so here I'm putting I tilde J without the C here. So this is going to differentiate the matrices equivalence relations. Remember, the conjugacy class of matrices was denoted this, like that with a C there. But here for the fractional O-ideals, I'm going to just put a tilde here, like that. So this is just kind of differentiating the two equivalence class relations here. So anyways, we say that I is equivalent to J, and it's denoted I tilde J. If I is equal to X times J for some X in K star, or for some non-zero X in K, It's straightforward to check, actually, just like the conjugacy relation, that this relation is also an equivalence relation. And so we'll denote by bracket I to be the equivalence class, which is represented by the O-fractional ideal I. So here, remember in this setting, we denoted the equivalence class represented by A as just A. We put an A here, but we put a little C there. Over here, we're just going to put bracket I like that. So that's just trying to not get confused about the terminology here. So anyways, it's easy to show actually that, well, let's see, let's get back to here. So, okay, so I is the equivalence class, which is represented by the O-fractional ideal I. We call these equivalence classes O-ideal classes, right? And we'll denote by class of O, or CL of O, to be the set of all O-ideal classes. In fact, you can actually show, and it's pretty easy to show, that the CL of O is none other than the set of isomorphism classes of O-fractional ideals. In other words, the relation I is equivalent to J is equivalent to saying I is isomorphic to J as O modules. To see this, if I is equivalent to J, so I is equal to xj for some x and k that's not 0, then the multiplication by x map, and we denote this by n sub x here, is given by, it takes a y and I, and it sends it to xy. This is an O module isomorphism from I to j. So that's one direction. So if this is equivalent, if I is equivalent to j, then we get an isomorphism, or an O isomorphism from I to j like this. The converse says if var phi is a O module isomorphism from I to j, then we first claim that var phi of y over y is equal to var phi of z over z for any non-zero y and z. So first we're going to show this, and we'll show why that will imply var phi is just a multiplication by some non-zero x and k. But first we show this. To see this, we choose a non-zero gamma and O, so that gamma y and gamma z both belong to O. So this is this is also an equivalent condition for O, or I mean for I to be a fractional O ideal. It means that you can always multiply each element by some other element to get him into O. So this is just a such a choice is possible since I is a fractional O ideal. Then we observe that, so we do this relation here, right here. So gamma times this guy right here is equal to, so we first add the var phi over y with the var phi over z here. Then we distribute the gamma inside like this. And now the key fact here now is that I can pull the gamma z inside of the var phi now, because gamma z belongs to O, right? Gamma z belongs to O, and the same thing for gamma y. So I can't pull, so at this step right here, I cannot pull the z inside the var phi, because z may not be in O. Z may be in K, but it may not be in O. And var phi is supposed to be O linear, which means you can pull things that are inside O inside the var phi here. But that's why we need this gamma here, in order to get gamma z and gamma y, in order to pull in gamma z into var phi like this and gamma y into var phi like this. And then you're allowed to cancel like this. And so the final step is that, so this gamma times this guy here is equal to 0. And since gamma is non-zero, and since we're in an integral domain, this implies that this guy here must be 0. So now we write, so just write x equal to var phi of y over y. And like we just showed here, actually you can choose any y, any non-zero y and I, you'll get the same x here. So then for any non-zero z and I, we have var phi of z is equal to var phi of z over z times z, which is equal to var phi of y over y, about what we just showed, times z, which is equal to x times z, which is equal to the multiplication by x map of z. And finally, since var phi of 0 is equal to m sub x of 0, this is pretty clear. We actually do have var phi is equal to m sub x. So I is equivalent to j, and that's what we just showed here. So we just showed that this is actually, this equivalence right here really is going to be the same thing as the, this is essentially isomorphism, of O modules. So we're going to use that in the coming proof that we're going to do here in a second. But so this is, so now that I've kind of introduced or recalled some notation, let me go ahead and state the main theorem. So here's the main theorem. So let f of t be a monic irreducible polynomial of degree n, and let alpha be a root of f of t. Then we have a bijection. So here, the left-hand side are the conjugacy classes of matrices with characteristic polynomial f, with coefficients or the entries of the matrices are in Z. And over here to the right, these are the O-ideal classes in Z, for Z of alpha. So these are or you could think about CL of Z of alpha as the isomorphism classes of fractional Z of alpha ideals. So these things are equivalent, or I mean, there's a bijection between these two guys here, and that's what we're going to prove here now. So we want to define capital psi from CL of Z of alpha. So these are the O ideal classes of Z of alpha, or the Z of alpha ideal classes, to the conjugacy classes of matrices with characteristic polynomial f. And we do this as follows. So first, let A be a let math frac A be a Z of alpha fractional ideal. So from the structure of finitely generated torsion-free modules over Z, we know that A is a finitely generated free Z module of rank n. So this is kind of like what's going to help make this conjugacy, this isomorphism work. Really, this is a really nice property of fractional O ideals, or fractional Z of alpha ideals in this case, being free and of rank n. So this is very nice property. So we're about to show why this is going to help us define this capital psi here. So we choose an ordered basis of math frac A as a free Z module. So here is, so let's say that we choose this guy right here. So we're going to put bold A is equal to this ordered basis alpha 1 of alpha sub n. Okay? And we're going to let m sub alpha from math frac A to math frac A be the multiplication by alpha map, right? So this is how we kind of denote the multiplication by alpha map here. So m sub alpha of x is equal to alpha x for all x in math frac A. Okay? And our notation here is we're going to let bracket m sub alpha here, this guy right here, this is the matrix representation of m sub alpha with respect to the basis bold base A. So the notation here will be useful. You'll see how the notation will be useful later on. Essentially, what this means is that the I, jth entry of this matrix here is given by a sub j, I, and z, where this a sub j, I comes from this relation here. So this is the usual matrix representation map that we kind of do in linear algebra here. And the point is that a sub j, I is uniquely determined since alpha sub this bold base A guy is a basis, right? So this is a linearly independent set of elements. That's what makes this alpha sub j, I here uniquely determined. If bold A prime is another ordered basis of math frac A as a free Z module, then the change of basis matrix from bold face A to bold A prime is given by, so here we use this notation over here. So 1 sub math frac A is just the identity map on math frac A. And here we're saying we're going from A to A prime. And essentially, when we do this calculation here, all this calculation here follows from basic kind of linear algebra that we kind of do. Essentially, this whole thing works because of, again, this is free Z module condition up here. Right? This is a very nice property of fractional O ideals. So anyway, in other words, what I'm trying to say here is that changing the basis from bold A to bold A prime corresponds to conjugating this matrix representation here to this matrix representation here. So, okay, so with all of this understood here, okay, so I just wanted, this is kind of a little bit preliminary here. So now I'm ready to define what capital psi is. Okay, so capital psi, so this is how it's defined. We take an ideal class in Z of alpha, bracket math frac A, and we're going to send it to the conjugacy class of this matrix representation for alpha with respect to this basis boldface A. Now, we have to check that this guy here is well defined. So in our construction of capital psi, we had two choices that we kind of made here. One choice was the choice of the ordered basis for math frac A as its free Z module, where we chose bold A, right? But this is what this discussion up here was about, what I just mentioned up here. Because if I change the basis from bold A to another basis, then you would just get a conjugate. So if I change the basis from bold A to bold A prime like this, you would just get a conjugate matrix, right? So A to A, the matrix representation of m sub alpha with respect to the basis bold A is going to be conjugated, or a conjugation of the matrix representation of m sub alpha with respect to the ordered basis bold A prime, right? So in fact, that's why we put this conjugacy class right here, this sub C here. This makes it so that you get the same conjugacy class. You know, it doesn't matter what basis you choose. So that kind of takes care of the choice of the basis. The other choice that we made was we chose with the choice of a representative of the Z of alpha ideal class bracket math frac A, where we actually just chose bracket A. So let B, so math frac B be another coset representative of the coset bracket math frac A. So B is equivalent to A. This means that there's an X in Q of A, Q of alpha star, or there's a non-zero X in Q of alpha, such that B is equal to XA. So the point is that actually, if you have this here, then here our bold A is just a fixed choice of a basis for the Z module, right? So we just showed that it doesn't matter which one you choose. But actually, X times A is a basis for B as a free Z module. So to see this, obviously it spans B as a Z module, since B is equal to XA. And also it's Z linearly independent because it's Q linearly independent, as multiplication by X is a Q isomorphism. So in fact, you can show, I mean, it's pretty simple to show that this matrix multiplication map with respect to this bold A basis is actually the same as this matrix representation map of m sub alpha with respect to the X times A basis. It's pretty easy to show that this follows from the fact that these things commute, or that AX is equal to XA. And this guy here is just going to be exactly this bold B here. We just call it bold B if you want. The point is that I'm able to choose a basis, an ordered basis for math frac B over here, such that the matrix is the same matrix right here. So the point is that this guy here is well defined. Number one is well defined. It doesn't depend on the ordered basis that you choose, the A, and it also doesn't depend on the choice of the coset representative of this ideal class right here. Okay, so now we are going to show that capital psi here is injective. Okay, so let bracket A and bracket A prime be two fractional O ideals. So here this should say Z of alpha ideals here. So this should be Z of alpha ideals, right? Because that's the order that we're talking about here. And let bold A and bold A prime be ordered bases for A and A prime as free Z modules respectively. Suppose that capital psi of this equivalence class is, or this class is equal to capital psi of this class here. So what I'm trying to show is that I want to show that that bracket A is equal to bracket A prime, because that will show that that capital psi is injected. So what does it mean for capital psi of bracket A to be equal to capital psi of bracket A prime? It means that there's a U in GL and Z, such that U conjugates this guy, right? This M sub alpha, this matrix representation map of M sub alpha with respect to bold A, to this matrix over here, M sub alpha with respect to bold A prime, because that's what that's what it means to be equal to each other here. So let bracket sub A, bold A, go from A to Z to the N be the standard column representation map for A. So that is bracket A is a unique Z linear map which sends alpha sub I to E sub I. That is where E sub I comes from the standard ordered column basis for Z to the N. We use bold E to denote this standard ordered column basis for Z to the N as a free Z module. So essentially what we're doing, what I'm saying here is I'm saying you're going to send, so this map here goes from A, math frac A to Z to the N, like that. And it's going to send alpha sub I, it's going to map it to this column vector here with a 1 here and then a dot and a 0 like that, right? So this guy here is, so 1 in the ith spot. 1 in ith spot. And 0 everywhere else. So that's the idea. So yeah, so bracket sub A is that standard column representation map. This is a Z linear map. And then also we do the same thing for bracket sub A prime. Then we observe that when we compose brackets of A with U, where U is this conjugating matrix over here, with brackets of A prime, we get a Z linear isomorphism from A to A prime, right? So this is isomorphism as Z modules. But in fact, we actually have an isomorphism of Z of alpha modules. And the reason that we see that is because we show that M sub alpha commutes with this map here. So if we can show that M sub alpha commutes with this map here, and that's what this is done in this calculation here. You swap the M sub alpha with this guy first, and then you swap the M sub alpha with this U here, and you get to this guy, and then you swap it with this guy here. This shows that these are actually, that this map here is actually a Z of alpha isomorphism. So, and then that's why we were talking about earlier up here, we said that this equivalence relation here, being equivalent as O ideal classes, that's just being isomorphic as O modules. Now that we can come back down here and we can kind of mention here now that isomorphic fractional Z of alpha ideals, well, those are precisely the scalar multiples of each other. So like A prime is equal to XA, that's what we have. So this is an isomorphism of Z of alpha fractional ideals, which means that A prime is equal to XA for some X non-zero and Q adjoining alpha. So in particular, they are the same class, and so capital psi is injected. So that's showing that capital psi is injected. Now we want to show that capital psi is surjective. So here we let A be a matrix, an M sub n a Z, and I go ahead and tell you that its entries are the form A sub ij, so these are integers here. And suppose, so this is a matrix in M sub n a Z such that the characteristic polynomial of A is equal to f of t. So we will find, so to show that capital psi is surjective, we will find a Z of alpha fractional ideal A, and an ordered basis bold A of A as a free Z module such that A is the matrix representation with respect to multiplication by alpha of this ordered basis A. So that will show that this is the surjective map here. So first, we make q to the n into a q to the alpha, q of alpha vector space as follows. So let x be in q of alpha and let b be in q to the n. We choose g of t and q of t such that g of alpha is equal to x. So such a choice is possible because this q of alpha here, this alpha here is an algebraic integer, so q of alpha, q parentheses alpha is equal to q bracket alpha. And now we define scalar multiplication of q of alpha on q to the n by, so we put x c dot b is equal to g of a b. So again, so to define this action x dot b, we just choose a g of t in here in q of t, and then we just substitute in, instead of t, we put in the matrix A, and we let it act on v. Now, obviously, this choice of this action that we just defined here, it involves a choice named g of t. So in order to show that this is well defined, we have to consider another choice. So that's what we do here. So we made a choice such that g of alpha is equal to x. So suppose h of t is also in q of t, and suppose that h of alpha is equal to x. So this h of t is another choice such that h of alpha is equal to x. Then g minus h of alpha, so alpha is a root of g minus h. And this implies f divides g minus h. And this is where we use the hypothesis that f, so f is the minimal polynomial of alpha over q, since it's monic, so we use, that's an irreducible with root alpha. So that's where we use this hypothesis here, right? So right now, all we're considering is we're considering f to be a monic irreducible polynomial of degree n, and we're having alpha be a root. So we're considering these specific conjugacy classes of matrices where f has these properties, and that's where we just use that property here. So going back to the proof, so okay, so f divides g minus h, so therefore g of a is equal to h of a as matrices, because essentially if f divides g minus h, right, then you have fp is equal to g minus h, right? And so basically when we apply a here to both sides, we apply the matrix A to both sides here, the f of a goes away, and so you can just apply a, so apply, so this should be t equals a here. So apply, let's just say evaluate t equals a here. So I'm not showing a t for the g and h here, but you evaluate t is equal, so you set t equal to a here, and this becomes 0 because f of a is equal to 0, and this would be equal to g of a minus a, h of a. So that's essentially what's going on there. So okay, so therefore g of a is equal to h of a as matrices. So this is well defined because you just get the same thing. G of a is equal to h of a. It's also straightforward to check that this action here gives you a q to the q of alpha vector space structure on q to the n. So it satisfies all the required properties needed for that to happen, like left distributivity and right distributivity and so on and so forth. And in fact, and also more importantly, actually, is that you can pull alpha out of this scalar multiplication map. So this actually, so actually restricting scalars of this guy here, so considering x is not in q of alpha, but say z of alpha, this also gives q to the n a z of alpha module structure. In fact, if v belongs to z to the n, so I'll keep it up here, so if v belongs to z to the n, then alpha dot v, the alpha c dot v is equal to ab. Well, this is in z to the n because a has integral entries. So that's what we assumed. A was a matrix with entries, integers. So z to the n is a z of alpha submodule of q to the n. So we started with q to the n being a q of alpha vector space. Then we restrict to scalars. to get q to the n be a z of alpha module. And then we showed here that we can restrict the q to the n to z to the n, and we still get a z of alpha submodule of q to the n. And by basic dimension theory of vector spaces, q to the n is a one-dimensional q of alpha vector space. Okay, so what does it mean that q to the n is a one-dimensional q of alpha vector space? It means that for any non-zero v naught and q to the n, the q of alpha linear map var phi sub v naught from q of alpha to q to the n given by this guy here. So we fix x here, or we fix v naught here, and then we act on x on the left, right? So this gives us a q alpha isomorphism from q of alpha, right? So we send x to this guy here, which belongs to q to the n. So this is a q of alpha isomorphism of these one-dimensional vector spaces. So if we let bold e sub 1 at the e sub n denote the standard ordered column basis for q to the n as a q vector space, then there exists unique alpha sub I in q of alpha such that this q of alpha isomorphism, really, so it's obviously a q isomorphism. It'll send alpha sub I to e sub I for all 1 less equal to I less equal to n. In particular, bold A, which is equal to alpha 1 to alpha n, is an ordered basis for q of alpha as a q vector space. That we need that, right? So now we let we let A, we define this guy here, which right now we know that he's a lattice, but soon we'll know that he's a fractional z of alpha fractional ideal. We just define this math frac A to be the sum or the z span of these alpha sub i's. So actually, A is a z of alpha fractional ideal, and this actually follows from the fact that alpha sub I is in math frac A for all 1 less equal to I less equal to n. So why do we have this? Why is this guy here? Well, this follows from this calculation here, essentially. So that's essentially the idea. Okay, so in particular, so what we've just done here is we've constructed a z of alpha fractional ideal, math frac A here, and we've got a ordered basis right here, this alpha sub I here, or this bold A here. This is an ordered basis for this math frac A as a z module, or as a free z module. And in fact, this relation here, so actually when you do this calculation here, you realize that alpha times alpha sub I is equal to a sub ji alpha sub I. Where did these a sub ji's come from? Well, they came from this matrix A here. So in fact, when you do this calculation here, you see that actually A is exactly the matrix representation of m sub alpha with respect to the ordered basis A. So we have realized A as a matrix representation for m sub alpha on a z of alpha fractional ideal. Thus, capital psi is on 2. So that's the proof of the theorem. So let us look at an example and see how this thing kind of applies here. So let f of t be equal to t squared plus 5. Right, so this is obviously is irreducible over q, and square root negative 5 is a root of this guy here. So what we want to do is we want to count the number of conjugacy classes of matrices with entries in Z whose characteristic polynomial is f. Right, that's what we want to count. We will find, so not only are we going to count that, but we're also going to find the cosec representative of each conjugacy class in C2Z, F. Know that f is a monic irreducible polynomial over Z. Like I said, it's a monic irreducible polynomial over Z, and square root negative 5 is a root. So we can apply the previous theorem that we just proved. So the ring Z squared negative 5 has class number 2, which means that that's the size of class number 2 means that's going to be the size of CL of Z alpha. So that's what we're saying. I'm just saying that this is that's what we mean by class number. So there's precisely two Z of joined square root negative 5 ideal classes. And so that means that the number of conjugate Z classes of matrices with characteristic polynomial F is precisely 2. There's only 2 conjugate classes of matrices with that characteristic polynomial. The ideal classes in Z squared negative 5, so we can represent them by these 2 fraction ideals. In fact, these are these integral ideals here. So this is the first one is Z squared negative 5. And the second one is going to be this prime ideal, which sits over 2, is given by 2, 1 plus square root negative 5. Okay. So an ordered basis for Z squared negative 5 is given by 1, square root negative 5. And an ordered basis for P2 is given by this guy right here. Now, in general, an ordered basis for P2 will not be just 2, 1 plus square root negative 5. It does happen to be that case here. But usually you have to check that these are actually the ordered bases for these guys as a free Z module. But in this case, it's pretty clear. These are going to be the ones. So what do? So we calculate the matrix representation of square root negative 5 with respect to the ordered basis A1 first, right? So that's what this calculation does. And we see that this guy here, the matrix representation of the multiplication map by square root negative 5 with respect to the ordered basis bold A1 is equal to this matrix here. And we do a same calculation with this ordered basis for the A2 ordered basis like this, okay? So P2 and 1, these represent different ideal classes in Z squared negative 5. So therefore, these matrix representation maps, or these matrices, bracket M sub square root negative 5 A1 and bracket square root negative 5 A2, these are going to represent different conjugacy classes of matrices over with the interest in Z with characteristic polynomial F. So thus, and these are all of them actually. These are all the classes because these are all the ideal classes. These represent all ideal classes, so therefore these 2 matrices represent all conjugacy classes. So therefore, if A is any matrix with coefficients in the ring of integers and it has a characteristic polynomial F of t, then it must either be conjugate to this matrix or this matrix here. So let's so now let P7 be this prime ideal here. So it's 7, 3 plus square root negative 5. So this is the prime ideal in Z squared negative 5, which sits over 7. It turns out that P7 is equivalent to P2, and you can see this by this relation here. So P7 is equal to 3 minus square root negative 5 over 2 times P2. And an ordered basis for P7 is given by, I think this needs to be plus. This should be plus, I think, right here. Yeah, let's put plus. Okay, for now. I'm not actually, yeah, no, actually that's right. That's what I want there. Okay, so that's the ordered basis for P7 there, actually. So I think this one here, let me see here. So this is square root 35, 2, 3. Okay, this one should be minus here. Yeah. Okay, so that one should be minus there. Okay, so this one should be 7, 3 minus square root negative 5 here. And we'll see in a second, actually, it's kind of interesting that, P bar 7 actually is going to be the plus one, but we don't want that one right now. This is P bar 7, that's equal to 7, 3 plus square root negative 5. So that's P bar there. We want P sub 7 with the minus here though. So this one's equivalent to P2, and that's, you can show that this is the case right here. You can multiply this guy by this P2 and you get P7. So an ordered basis for P7 is again, it's given by the generators of the ideal, but let me just remark again that in general, the generators of the ideal will not give you an ordered basis like it's doing for my examples here, but that's a side point, I guess. By straightforward calculation, we calculate the multiplication by square root negative 5 map. Essentially the ordered basis here, that's the matrix representation here, that's given by this matrix here. So we do the same calculation that we did up here. Thus, these two guys are conjugate, right? That's what it means. If the ideal class, so we know that P7 is equivalent to P2, then that means that their matrix, the matrix representations for P7 and P2, they have to be conjugate right here. All right, that's what it means. But now we want to find a matrix which actually does the trick, which actually conjugates this guy to this guy. So how are we going to do that? Well, we first change the ordered Z basis A2 of P2 to the ordered basis A2 prime. So all we do here, so we go from, let's see if we can go back up here for a second. So A2 initially is defined to be 2, 1 plus square root negative 5. But now we're going to do a change of basis. We're going to change A2 to A2 prime to 2, 3 plus square root negative 5. So all we're doing is we're adding a 2 to the right here. So that corresponds to, when you calculate the change of basis matrix from A2 to A2 prime, it's given by this matrix here. So we do the same thing with the ordered Z basis A7 of P7, and we change that one to A7 prime to this guy here. So this is just a swap. So initially A7 is defined by 7, 3 minus square root negative 5. Well, now we want to swap it like this, right? And the change of basis matrix from A7 to A7 prime is given by this, this matrix here. Now, so we do those change of bases matrix, or we change those ordered bases first. And then what we check now is we check that this 3 minus square root negative 5 over 2 map, when we multiply it by A2 prime, so remember this is just like an isomorphism kind of guy here. When we multiply by A2 prime, we get A7 prime. So that's why we changed the A2 basis to A2 prime and A7 basis to A7 prime, is so that we can actually literally get A7 prime from A2 prime by just multiplying this guy to A2 prime to get A7 prime. And so what that does is, this. So we start with the matrix here, -1, 2, -3, 1. That's the matrix representation for m squared negative 5 respect to A2. So what we do first, we go from here to here. We this is the changing the basis from A2 to A2 prime. That's what we do here. So we change for A2 to A2 prime here. So let's just put change basis. So that's what we're doing here. So that's how we get from the A2 to A2 prime here. And now from this step to this step, this follows from the fact that, let me see if I wrote this. Okay, it's 3 minus square root negative 5. This follows from the fact that 3 minus square root negative 5, negative 5 over 2, A2 prime is equal to A7 prime. So that's why we changed the basis, because now multiplying A2 prime by this 3 minus square root negative 5, it gives you precisely that guy. And it's easy to show that these matrix representations, these are the same matrices right here. So that's going to be, that's where we're just kind of replacing A2 prime here with A7 prime here. Okay, so now from this step to here, so we just change, so now that we have that, we change basis again, right? So we just change basis here. So we change basis again. And so after we do that, we kind of combine these together. We write them as actual matrices here that we kind of calculated earlier, and that's what it's going to be. So this is the matrix that does the trick right here. This is the matrix that conjugates, it would conjugate this 7, 3, -7, 2, -3 to this guy over here. So that's how we kind of calculate the matrix which does the trick. And so to end this presentation here, I just summarized some of the calculations that we did here with in this table. So these guys here are equivalent. So these are equivalent. Equivalent. This is right, equivalent here. So what I mean by that is that the ideal class for P2 is the same as the ideal class for P7, and also the the conjugacy class of this matrix here, is the same as the conjugacy class of this matrix here. But for 1, we don't have the same, right? We don't have, we cannot conjugate 0, this matrix here, to this matrix here. But let me just mention real quick, though, that we do have, let me just finish this note here. We do have 0, -5, 1, 0. So this is conjugate to this guy, 2, -3, over Q, right? So we can conjugate 0, -5, 1, 0 to -1, -3, 2, 1. But we need to use in order to conjugate it over to this guy, we have to use a matrix from Q. And that follows from basic linear algebra. So yeah, so that's going to be, that's pretty much sums up my talk here. And I hope you enjoyed it. And yeah, so just let me know what you think, give me some feedback or anything. And thank you for listening. So let me just end this now.